What if I told you that right above your head, scattered across the infinite darkness of space, there are worlds so similar to Earth that they might harbour oceans, continents, and perhaps even life itself? What if humanity has already discovered nearly 6,000 of these alien worlds, each one a potential home for civilizations we can barely imagine? The numbers are staggering. As of 2025, astronomers have confirmed the existence of almost 6,000 exoplanets, planets orbiting stars other than our Sun. But here's what will absolutely shock you. We've barely scratched the surface. Conservative estimates suggest there are more than 100 billion planets in our galaxy alone. That means for every grain of sand on every beach on Earth, there could be hundreds of alien worlds waiting to be discovered. Tonight we're going to take you inside the greatest treasure hunt in human history. This isn't science fiction, this is science fact. We're going to reveal how a small group of determined scientists revolutionized our understanding of the universe, how they developed techniques so sensitive they can detect the gravitational tug of a planet smaller than Earth from distances of hundreds of light years away, and why the next decade might finally answer humanity's most profound question: are we alone? But first, let me share something that will fundamentally change how you see the night sky. Every single star you can see with your naked eye, all 9,000 of them visible from Earth, statistically harbors at least one planet. When you look up tonight, you're not just seeing distant suns. You're seeing potential solar systems, possible Earths, maybe even worlds where at this very moment other beings might be looking back at us. The story you're about to hear spans 3 decades of revolutionary discoveries. It involves Nobel Prize-winning breakthroughs, space telescopes worth billions of dollars, and detection methods so ingenious they border on magic. We'll explore how astronomers learned to catch the faintest whispers of light from worlds trillions of miles away, how they decoded the secrets hidden in starlight, and how they transformed astronomy from a science of speculation into a precise tool for mapping entire galaxies of planets. This journey will take us from the first shocking discovery of alien worlds around dead stars to the launch of space telescopes that monitor hundreds of thousands of stars simultaneously. We'll witness how citizen scientists working from their home computers made discoveries that eluded professional astronomers, and we'll explore cutting-edge techniques that can reveal not just the existence of distant planets, but their atmospheric composition, surface temperatures, and potential for hosting life. The implications of this research extend far beyond astronomy. Every new planet we discover reshapes our understanding of planetary formation, stellar evolution, and the fundamental processes that govern our universe. These discoveries force us to confront our place in the cosmic order and challenge our assumptions about what makes a world habitable. But, perhaps most importantly, we're approaching a historical inflection point. Within the next 10 to 15 years, new telescopes and detection methods will give us the capability to analyze the atmospheres of Earth-like planets around nearby stars. For the first time in human history, we may detect the chemical signatures of life itself in the atmosphere of an alien world. The race to find Earth 2.0 has begun, and the winner will claim perhaps the greatest prize in scientific history, proof that life exists beyond our pale blue dot. To understand the magnitude of what we've accomplished in exoplanet science, we need to step back and appreciate just how recently this field even existed. 35 years ago in 1990, we knew of exactly 9 planets in the entire universe. 9. All of them orbited our Sun, and the idea of finding planets around other stars seemed so technically impossible that most astronomers considered it a problem for future generations to solve. The challenge was fundamentally one of scale and contrast. Imagine trying to spot a firefly hovering next to a lighthouse from a distance of 1,000 miles. That's roughly analogous to the difficulty of detecting an Earth-sized planet orbiting a Sun-like star from typical interstellar distances. Planets don't generate their own light, they merely reflect the light of their parent stars. An Earth-like planet orbiting a Sun-like star appears roughly 10 billion times fainter than the star itself. But human curiosity about other worlds stretches back millennia. Ancient Greek philosophers speculated about the plurality of worlds. Giordano Bruno, the 16th century Italian philosopher, was burned at the stake partly for asserting that the stars were distant suns surrounded by their own planets. Even as recently as the 1980s, serious astronomers debated whether planetary systems were common or whether our solar system might be a cosmic fluke. The breakthrough came from recognizing that while we couldn't see the planets directly, we might detect their gravitational influence on their parent stars. Every planet tugs on its star, causing the star to wobble slightly as both objects orbit their common center of mass. For a Jupiter-mass planet orbiting close to a Sun-like star, this wobble causes the star's velocity to change by about 50 meters per second, roughly the speed of a bicycle. Detecting such minute velocity changes required revolutionary improvements in spectroscopy. Astronomers needed to measure Doppler shifts in stellar spectra with unprecedented precision. The Doppler effect, the same phenomenon that makes an ambulance siren change pitch as it passes you, causes the wavelengths of stellar light to shift slightly redward when a star moves away from us and blueward when it moves toward us. By the late 1980s, teams of astronomers were pushing spectroscopic precision to its limits. Swiss astronomers Michel Mayer and Didier Queloz developed new techniques using cross-correlation methods to achieve velocity measurements accurate to within 15 meters per second. American teams led by Jeff Marcy and Paul Butler were achieving similar precision using iodine absorption cells as wavelength calibrators. The stage was set for a revolution, but nobody predicted how quickly it would unfold or how dramatically it would transform our understanding of planetary systems. Before we could begin searching for Earth-like planets in earnest, astronomers needed to define what exactly they were looking for. The concept that emerged as central to this search is the habitable zone, colloquially known as the Goldilocks zone, the region around a star where conditions are just right for liquid water to exist on a planet's surface. The physics underlying the habitable zone is actually quite complex. It depends not only on the star's luminosity and the planet's orbital distance, but also on the planet's atmospheric composition, greenhouse effect, albedo, reflectivity, and even its orbital eccentricity. For our Sun, the habitable zone extends roughly from the orbit of Venus, too hot with surface temperatures around 460 degrees Celsius, to slightly beyond Mars, too cold, with average surface temperatures around -60 degrees Celsius. Earth sits comfortably within this zone at 1 astronomical unit from the Sun, a distance that allows water to exist in all three phases: solid ice at the poles, liquid oceans covering 70% of the surface, and water vapor in the atmosphere. This liquid water is crucial because it serves as the universal solvent for biochemistry as we understand it. But the habitable zone is not a fixed boundary. It evolves as stars age and change their energy output. When our Sun was young 4 billion years ago, it was about 25% dimmer than it is today. This creates what astronomers call the faint young sun paradox. Early Earth should have been frozen solid, yet we have geological evidence of liquid water dating back nearly 4 billion years. The resolution likely involves a stronger greenhouse effect in Earth's early atmosphere, possibly due to higher concentrations of carbon dioxide or methane. For other types of stars, the habitable zone looks very different. Red dwarf stars, which make up about 75% of all stars in our galaxy, are much cooler and dimmer than our Sun. Their habitable zones are correspondingly closer to the star, typically within about 0.3 astronomical units. This proximity creates interesting complications. Planets in the habitable zones of red dwarfs are likely tidally locked, with one hemisphere permanently facing the star and the other in eternal darkness. More massive stars than our Sun burn hotter and brighter, pushing their habitable zones outward. However, these stars also have much shorter lifespans. A star twice the mass of our Sun might only remain stable for about 1 billion years, possibly insufficient time for complex life to evolve, given that it took nearly 4 billion years for complex multicellular life to emerge on Earth. The habitable zone concept provided astronomers with their first concrete target in the search for potentially life-bearing worlds. Rather than simply cataloguing any planets they could find, they could focus their efforts on identifying planets within these special regions, where the fundamental requirements for life as we know it might be satisfied. The first confirmed discovery of planets beyond our solar system came from the most unexpected source imaginable: a dead star spinning at 600 rotations per second, located over 1,000 light-years from Earth. In 1992, astronomers Alexander Wolszczan and Dale Frail announced they had detected not one but two planets orbiting a pulsar designated PSR 1257+12. To appreciate how revolutionary this discovery was, you need to understand what a pulsar actually is. When a massive star, at least 8 times more massive than our Sun, reaches the end of its life, it undergoes a catastrophic collapse. The core crushes down to a sphere only about 20 kilometers in diameter, but containing more mass than our entire Sun. This creates a neutron star where matter is compressed to densities so extreme that a teaspoon would weigh as much as Mount Everest. Many neutron stars emit beams of radiation from their magnetic poles. As the star spins, these beams sweep across space like lighthouse beacons. When such a beam happens to point towards Earth during each rotation, we detect regular pulses of radio waves, hence the name pulsar. PSR 1257+12 was discovered to pulse every 6.2 milliseconds with clockwork precision. But Wolszczan and Frail noticed something extraordinary in their timing data. The pulses weren't arriving with perfect regularity. Instead, they showed tiny variations, sometimes arriving a few microseconds early, sometimes late. The pattern of these timing variations was exactly what you would expect if the pulsar was moving back and forth due to the gravitational tugs of orbiting planets. The analysis was painstaking and required years of precise observations. The timing variations revealed 2 planets with masses approximately 4 times and 3 times that of Earth, orbiting the pulsar every 67 days and 98 days respectively. Later observations confirmed a 3rd planet in the system. This discovery was simultaneously thrilling and sobering. Thrilling because it proved definitively that planets could form around other stars, our solar system was not unique. Sobering because these worlds represented perhaps the most hostile environments imaginable for life. The radiation environment around a pulsar is millions of times more intense than anything in our solar system. Any planets there would be continuously bathed in lethal high-energy particles. The pulsar planet discovery also raised profound questions about planetary formation. How could planets survive the supernova explosion that created the neutron star? The most likely explanation is that these planets formed from debris after the supernova, condensing from the heavy elements expelled during the stellar explosion. This suggested that planet formation might be far more robust and varied than astronomers had previously imagined. More importantly, the pulsar planet discovery demonstrated that the techniques existed to detect planets around other stars. If planets could be found around exotic objects like pulsars using radio timing methods, then surely planets around normal stars could be detected using other techniques. 3 years after the pulsar planet announcement, Michel Mayor and Didier Queloz were conducting a systematic survey of Sun-like stars using the LOD spectrograph at the Observatoire de Haute-Provence in France. They were measuring radial velocities, the component of stellar motion toward or away from Earth, with unprecedented precision, searching for the telltale Doppler signature of orbiting planets. On October 6, 1995, they announced a discovery that would change astronomy forever. A planet orbiting the star 51 Pegasi, located about 50 light-years from Earth in the constellation Pegasus. The planet, designated 51 Pegasi b, was unlike anything in our solar system. The radial velocity measurements revealed a star wobbling with an amplitude of about 59 meters per second and a period of just 4.2 days. This implied a planet with at least half the mass of Jupiter, but orbiting its star at a distance of only 0.05 astronomical units, about 8 times closer than Mercury orbits our Sun. This discovery challenged fundamental assumptions about planetary system architecture. In our solar system, the small rocky planets orbit close to the Sun, while the gas giants reside in the outer regions. This arrangement made sense from theoretical models of planetary formation. Close to a young star, temperatures are too high for volatile compounds like water, methane and ammonia to condense. Rocky planets should form in the inner regions from refractory materials like silicates and metals, while gas giants should form farther out where ice and gas can accumulate. 51 Pegasi b shattered this paradigm. Here was a gas giant dubbed a hot Jupiter, orbiting so close to its star that its dayside temperature likely exceeded 1,000 degrees Celsius. The planet's year lasted just 4 days compared to Jupiter's 12-year orbital period. The implications were staggering. Either our theories of planetary formation were fundamentally wrong, or planetary systems could evolve in ways we hadn't anticipated. The most likely explanation involved planetary migration. The gas giant probably formed farther from its star, then gradually spiraled inward due to gravitational interactions with the surrounding disk of gas and dust. The discovery also validated the radial velocity technique as a powerful tool for planet detection. The method relies on measuring extremely small Doppler shifts in stellar spectral lines. As a planet orbits its star, both objects actually orbit their common center of mass, called the barycenter. For a Jupiter mass planet orbiting a Sun-like star, this causes the star to move in a small circle with a velocity amplitude of about 13 meters per second, roughly the speed of a fast bicycle ride. Modern spectrographs can detect velocity changes as small as 1 meter per second, enabling the detection of planets with masses approaching that of Earth. The technique works best for massive planets in close orbits which produce the largest stellar velocity variations. This creates an observational bias toward hot Jupiters, but improvements in instrumental precision have gradually extended the method's reach to smaller, more distant planets. The success of 51 Pegasi b sparked an explosion of planet discoveries using the radial velocity method. By 2000, astronomers had confirmed more than 50 exoplanets, almost all of them gas giants orbiting close to their parent stars. But radial velocity was just one tool in the emerging arsenal of planet detection techniques. The transit method, which would eventually become even more powerful than radial velocity, relies on detecting the tiny dimming of starlight when a planet passes directly between its star and Earth. The amount of dimming depends on the relative sizes of the planet and star. An Earth-sized planet transiting a Sun-like star blocks about 0.0084% of the star's light, a dimming of about 84 parts per million. To put this in perspective, detecting such a small change in brightness is equivalent to measuring the difference in the light from a car headlight when a coin is placed in front of it from a distance of several miles. The technical challenges are enormous, requiring photometric precision better than what could be achieved with ground-based telescopes due to atmospheric turbulence. The first confirmed transit detection came in 1999 when astronomers observed the previously known planet HD 209458b crossing in front of its star. This observation was revolutionary because it provided the first direct measurement of an exoplanet's size. Combined with the mass estimate from radial velocity measurements, astronomers could calculate the planet's density and infer its composition. Transit observations also opened up the possibility of studying exoplanet atmospheres. When a planet transits its star, a tiny fraction of starlight filters through the planet's atmosphere. By analyzing the spectrum of this transmitted light, astronomers can identify atmospheric constituents. The technique, called transmission spectroscopy, has revealed water vapor, sodium and other compounds in the atmospheres of several hot Jupiters. Gravitational microlensing represents another powerful detection method, particularly sensitive to planets at larger orbital distances. When a star passes precisely between Earth and a more distant background star, its gravity acts as a lens, magnifying the background star's light. If the lensing star has planets, they create additional magnification spikes in the light curve. Microlensing has unique advantages. It can detect planets at any orbital distance and is equally sensitive to planets around nearby and distant stars. The technique has revealed several Earth-mass planets and provided important constraints on the frequency of planets in the outer regions of stellar systems. Direct imaging, actually taking pictures of exoplanets, remains the most challenging detection method. The fundamental problem is contrast. Planets are millions to billions of times fainter than their parent stars. Advanced techniques involving coronagraphy, adaptive optics and space-based telescopes have enabled the direct detection of a few dozen young massive planets orbiting far from their stars. Each detection method has its own biases and limitations. Radial velocity favors massive planets in close orbits. Transits require edge-on orbital geometries and favor large planets around small stars. Microlensing works best for planets at intermediate distances. Direct imaging can only detect young, massive planets at large separations. Combining multiple methods provides a more complete picture of planetary system architectures. By 2009, astronomers had confirmed about 400 exoplanets, but they faced a fundamental limitation. Ground-based telescopes could not achieve the photometric precision needed to detect Earth-sized planets in Earth-like orbits around Sun-like stars. The solution required escaping Earth's atmosphere entirely. NASA's Kepler mission, launched on March 7, 2009, was humanity's first dedicated exoplanet hunting space telescope. The spacecraft carried a 0.95-meter telescope equipped with the largest digital camera ever launched into space, 95 megapixels spread across 42 charge-coupled device detectors. Kepler's strategy was elegantly simple, yet technically audacious. The telescope continuously monitored a fixed field of view in the constellation Cygnus, simultaneously observing approximately 150,000 stars for over 4 years. By measuring tiny periodic dimming events caused by transiting planets, Kepler could detect planets as small as Earth orbiting in the habitable zones of Sun-like stars. The mission's photometric requirements were extraordinary. To detect an Earth-sized planet transiting a Sun-like star, Kepler needed to measure brightness changes of about 0.0084% with a precision of about 20 parts per million. This demanded unprecedented stability in both the telescope optics and the digital detectors. Kepler's observing strategy differed radically from all previous planet surveys. Rather than targeting individual nearby stars, the mission observed a statistical sample of stars spanning a range of masses, ages, and metallicities. This approach enabled astronomers to determine the frequency and characteristics of different types of planets throughout the galaxy. The spacecraft's design reflected its singular focus. Unlike multi-purpose observatories, every component of Kepler was optimized for high-precision photometry. The telescope used a Schmidt design that provided a wide field of view while maintaining excellent optical stability. The focal plane was carefully designed to minimize systematic errors that could masquerade as planetary signals. Kepler's data processing pipeline was equally sophisticated. The mission generated approximately 160 gigabytes of science data annually, requiring automated algorithms to search for periodic transit signals among millions of stellar light curves. The challenge was not just detecting genuine planet signals, but distinguishing them from false positives caused by binary stars, stellar activity, and instrumental artifacts. Kepler's first confirmed planet, announced in January 2010, was Kepler 4b, a Neptune-sized world orbiting extremely close to its host star. But this was just the beginning. Over the next 4 years, Kepler would revolutionize our understanding of planetary systems by revealing thousands of new worlds with an unprecedented diversity of sizes, orbits, and compositions. One of Kepler's most significant early discoveries was Kepler 10b, announced in January 2011. This planet was remarkable for being the first confirmed rocky exoplanet smaller than Neptune. With a radius only 1.4 times that of Earth, Kepler 10b provided the first definitive proof that small rocky planets exist around other stars. The planet orbits its star every 0.84 days at a distance of only 0.017 astronomical units, closer than any planet in our solar system. Surface temperatures likely exceed 1,400 degrees Celsius, hot enough to melt rock. Despite its hellish conditions, Kepler 10b represented a crucial milestone, proof that Earth-sized rocky planets could form around Sun-like stars. Kepler 22b, announced in December 2011, captured global attention as the first planet confirmed to orbit within the habitable zone of a Sun-like star. With a radius 2.4 times that of Earth and an orbital period of 289 days, Kepler 22b occupies a position in its stellar system roughly analogous to Earth's position in our solar system. The planet's equilibrium temperature was estimated at -11 degrees Celsius, assuming an Earth-like atmosphere and no greenhouse effect. With a substantial atmosphere and greenhouse warming, surface temperatures could potentially support liquid water. However, the planet's relatively large size suggested it might be a super-Earth with a thick atmosphere and no solid surface, or possibly a mini-Neptune composed primarily of water and gas. Perhaps Kepler's most stunning discovery was the Kepler 11 system, announced in February 2011. This remarkable system contains 6 planets, all orbiting closer to their star than Mercury orbits our Sun. The planets range in size from 1.8 to 4.5 Earth radii and have orbital periods between 10 and 118 days. The Kepler 11 system challenged conventional wisdom about planetary system architecture. The 6 planets are packed so tightly that their orbits would fit easily within Mercury's orbit around our Sun. Despite this crowded configuration, detailed dynamical modeling showed the system is stable over billion-year timescales. The discovery suggested that compact multi-planet systems might be common throughout the galaxy. Kepler also discovered the first confirmed circumbinary planets, worlds orbiting both stars in binary star systems. Kepler 16b, announced in September 2011, orbits 2 stars every 229 days. The planet experiences double sunsets and sunrises, earning it the nickname Tatooine after the fictional planet in Star Wars. The existence of circumbinary planets was theoretically predicted but observationally challenging to confirm. The gravitational dynamics of such systems are complex, with the planet experiencing varying gravitational forces as the 2 stars orbit each other. The discovery of multiple circumbinary planets demonstrated that planet formation can occur even in these dynamically complex environments. The sheer volume of Kepler data presented an unprecedented challenge. The mission generated light curves for over 150,000 stars, each containing thousands of individual measurements taken every 30 minutes for 4 years. Automated algorithms could identify obvious periodic signals, but many interesting phenomena produced subtle or irregular patterns that required human pattern recognition to detect. NASA partnered with the Zooniverse citizen science platform to launch Planet Hunters, a project that enabled volunteers worldwide to search Kepler data for signs of transiting planets. Participants viewed stellar light curves through web-based interfaces, marking interesting features that might indicate planetary transits or other astrophysical phenomena. The citizen science approach proved remarkably successful. In January 2012, Planet Hunters volunteers Kian Jek and Robert Gagliano identified unusual transit signals in the Kepler light curve of star Chi-C 84628552. Follow-up analysis confirmed the discovery of Kepler 64b, also known as PH1b, a circumbinary planet orbiting 2 stars, which themselves orbit another pair of stars, creating a quadruple star system. Planet Hunters volunteers made several other significant discoveries, including planets missed by automated detection algorithms. The success of citizen science in exoplanet research demonstrated that human pattern recognition could complement sophisticated computer algorithms, particularly for identifying rare or unusual planetary configurations. The collaborative approach also had important educational benefits. Thousands of volunteers gained hands-on experience with real astronomical data, developing intuition about stellar variability, planetary transit signatures, and the challenges of exoplanet detection. Many participants went on to pursue further education or careers in astronomy, creating a new generation of scientists inspired by their direct involvement in discovery. The Planet Hunters project highlighted a broader trend in 21st century astronomy: the democratization of scientific research through digital technologies. With vast datasets publicly available online, motivated amateurs could make genuine contributions to cutting-edge research. This represented a return to astronomy's historical roots, when many discoveries were made by dedicated amateur observers. While Kepler revolutionized our understanding of exoplanet populations, its observing strategy had inherent limitations. The mission stared at a single patch of sky, monitoring stars that were typically quite faint and distant. Most Kepler planets orbit stars too dim for detailed follow-up studies of planetary atmospheres or precise mass measurements. NASA's Transiting Exoplanet Survey satellite, TESS, launched on April 18, 2018, was designed to address these limitations. Rather than focusing on a single field, TESS surveys 85% of the entire sky, searching for planets around the nearest and brightest stars. This strategy prioritizes finding planets suitable for detailed characterization rather than conducting comprehensive statistical surveys. TESS carries 4 identical cameras, each with a 16-degree field of view, mounted on a spacecraft in a unique elliptical orbit around Earth. The mission divides the sky into 26 sectors, observing each sector for 27 days before moving to the next. Over its 2-year primary mission, TESS monitored approximately 200,000 of the brightest stars in each sector. The mission's observing strategy reflects lessons learned from Kepler. While Kepler demonstrated that small planets are common, many of its discoveries orbit stars too faint for atmospheric studies with current telescopes. TESS prioritizes nearby, bright stars where detected planets can be subjected to detailed follow-up observations. TESS employs a rapid cadence observing mode, measuring stellar brightness every 2 minutes for approximately 20,000 specially selected target stars, and every 30 minutes for full-frame images of each sector. This high temporal resolution enables detection of short-period planets and provides detailed characterization of transit shapes. The mission's data processing pipeline builds on experience from Kepler but incorporates significant improvements. Automated algorithms search for periodic transit signals, while advanced techniques help distinguish genuine planetary transits from false positives caused by binary stars, stellar activity, or systematic instrumental effects. TESS began returning scientific data in July 2018, and its first confirmed exoplanet discovery was announced just 2 months later. Pi Mensae C, a super-Earth with a radius 2 times that of Earth and an orbital period of 6.3 days, became the first TESS object of interest, TOI, to receive planet confirmation. The discovery validated TESS's design philosophy. Pi Mensae is a bright nearby star only 59 light-years from Earth, making it an excellent target for atmospheric studies. The planet's size places it in the poorly understood transition region between rocky planets like Earth and gaseous mini-Neptunes. One of TESS's most significant early discoveries was 2RYY 700, a multi-planet system containing at least 3 confirmed planets. The innermost planet, TOI 700b, has a radius 1.07 times that of Earth and orbits its star every 9.8 days. This makes it one of the most Earth-like planets discovered by TESS in terms of size, though its close orbit results in surface temperatures exceeding 400 degrees Celsius. TESS also excelled at finding ultra-short period planets, worlds with orbital periods less than 1 day. These exotic objects, likely the remnants of larger planets that have been stripped of their atmospheres by intense stellar radiation, provide natural laboratories for studying planetary composition and evolution under extreme conditions. The mission discovered several notable multi-planet systems, including TOI 125, which hosts at least 3 sub-Neptune-sized planets with periods ranging from 3 to 19 days. Such tightly packed systems appear to be common around low-mass stars and provide important constraints on models of planetary formation and migration. TESS's focus on nearby bright stars enabled rapid follow-up observations using ground-based telescopes and spectrographs. The mission's discoveries could be quickly validated using radial velocity measurements, and the brightest systems became immediate targets for atmospheric characterization studies. The combination of Kepler and TESS observations, supplemented by ground-based surveys and other space missions, has provided the first comprehensive census of exoplanet populations. The emerging statistical picture reveals several surprising trends that challenge our understanding of planetary system formation. Perhaps the most significant finding is that small planets are extraordinarily common. Kepler observations suggest that approximately 20 to 50% of Sun-like stars host at least one planet between 1 and 4 times Earth's radius, with an orbital period shorter than 100 days. Extrapolating to longer periods and including M-dwarf stars, the galaxy likely contains tens of billions of potentially habitable worlds. However, detailed analysis reveals a puzzling gap in the size distribution of small planets. There appear to be relatively few planets with radii between 1.5 and 2 times that of Earth, a feature dubbed the radius gap or photoevaporation desert. The most likely explanation involves atmospheric escape. Planets initially form with substantial atmospheres, but intense stellar radiation strips away the atmospheres of smaller worlds, leaving behind bare rocky cores. The architecture of planetary systems also differs markedly from our solar system. While our giant planets orbit at distances of 5 to 30 astronomical units, most detected exoplanets orbit much closer to their stars. This reflects observational bias. Current detection methods are most sensitive to close-in planets, but it also suggests that inward planetary migration is common. Multi-planet systems detected by Kepler often show remarkable regularity in their orbital spacings and planetary sizes. Many systems contain chains of similar-sized planets with orbital periods related by simple ratios, suggesting they formed through orderly migration processes. This peas-in-a-pod architecture appears to be more common than the diverse planetary sizes found in our solar system. The metallicity dependence of planet occurrence provides important clues about formation mechanisms. Giant planets are preferentially found around metal-rich stars, consistent with core accretion models that require solid building blocks to assemble planetary cores. However, small planets show little correlation with stellar metallicity, suggesting different formation pathways for terrestrial and giant planets. The detection of exoplanets represents only the first step in understanding these distant worlds. To determine their potential for habitability and assess whether they might harbour life, astronomers must probe their atmospheric composition, surface conditions, and climate properties. This requires techniques that can extract information from the faint light signals we receive from exoplanetary systems. Transit spectroscopy has emerged as the most powerful method for studying exoplanet atmospheres. When a planet passes in front of its star, a tiny fraction of starlight filters through the planet's atmosphere before reaching Earth. Different atmospheric constituents absorb specific wavelengths of light, imprinting their spectroscopic signatures on the transmitted starlight. The technique requires extraordinary precision because the atmospheric signal is typically just a few parts per million of the total starlight. For a Jupiter-sized planet with a substantial atmosphere, the spectroscopic signal might reach 10 to 100 parts per million at certain wavelengths. For Earth-sized planets, the signals are 10 times smaller, pushing current observational capabilities to their limits. The first successful atmospheric detection was achieved in 2002 using the Hubble Space Telescope to observe the hot Jupiter HD 209458b. Astronomers detected sodium absorption in the planet's atmosphere, confirming theoretical predictions and validating the transit spectroscopy technique. This breakthrough opened an entirely new field of comparative exoplanet astronomy. Subsequent observations revealed water vapor, carbon monoxide, methane, and other molecules in the atmospheres of several hot Jupiters. These detections provided crucial insights into atmospheric chemistry, circulation patterns, and energy balance in exotic high-temperature environments unlike anything in our solar system. The technique works best for large planets with extended atmospheres orbiting bright nearby stars. Hot Jupiters represent ideal targets because their high temperatures cause atmospheric constituents to exist in gaseous form, and their large sizes produce detectable spectroscopic signals. Smaller, cooler planets present much greater observational challenges. Transit spectroscopy can also probe atmospheric properties through secondary eclipse observations. When a planet passes behind its star, the combined light of star plus planet is briefly reduced by the planetary thermal emission and reflected light. By comparing observations during and outside of secondary eclipse, astronomers can isolate the planetary contribution and study thermal emission from the planet's day side. The launch of the James Webb Space Telescope in December 2021 marked the beginning of a new era in exoplanet atmospheric studies. With its 6.5-meter segmented primary mirror and suite of infrared instruments, Webb possesses sensitivity more than 100 times greater than previous space telescopes for exoplanet observations. Webb's infrared capabilities are particularly crucial for exoplanet science because many important atmospheric molecules have their strongest absorption features at infrared wavelengths. Water vapor, carbon dioxide, methane, and ammonia all produce distinctive spectroscopic signatures in the 1 to 30 micrometer wavelength range covered by Webb's instruments. The telescope's first exoplanet observations, announced in summer 2022, demonstrated its revolutionary capabilities. Webb obtained transmission spectra of the hot Jupiter WASP-96b with unprecedented detail, revealing water vapor absorption across multiple infrared wavelengths and providing constraints on atmospheric temperature and cloud properties. One of Webb's most significant early results came from observations of the ultra-hot Jupiter WASP-18b. The telescope detected water vapor, carbon monoxide and carbon dioxide in the planet's atmosphere, while also measuring the planet's thermal emission spectrum. These observations revealed atmospheric temperatures exceeding 2,700 degrees Celsius on the planet's day side. Webb has also begun studying smaller planets that were beyond the reach of previous telescopes. Observations of the sub-Neptune K218b, a planet 2.6 times Earth's radius orbiting in its star's habitable zone, detected water vapor and possibly clouds in its atmosphere. While K218b is likely too massive to be truly Earth-like, these observations demonstrate Webb's capability to study atmospheric composition of potentially habitable worlds. The telescope's observations of the TRAPPIST-1 system have provided crucial insights into atmospheric evolution around red dwarf stars. TRAPPIST-1c, the second planet in this seven-world system, shows no evidence of a substantial atmosphere, likely due to atmospheric stripping by its host star's intense radiation. These results help astronomers understand which types of planets can retain atmospheres around the most common stars in our galaxy. Webb's unprecedented sensitivity enables detection of atmospheric constituents at concentrations as low as parts per million for favorable targets. The telescope can distinguish between different atmospheric scenarios: thick, hydrogen-dominated atmospheres, thin secondary atmospheres produced by volcanic outgassing, or completely airless worlds stripped bare by stellar radiation. The mission's planned 5 to 10-year lifetime will enable systematic atmospheric surveys of dozens of potentially habitable planets. Webb's observations are already constraining models of atmospheric evolution, greenhouse effects, and the conditions required for surface liquid water on exoplanets. While transit spectroscopy provides powerful insights into exoplanet atmospheres, the technique has fundamental limitations. It only works for planets that happen to transit their stars as seen from Earth, roughly 1% of all planetary systems. Moreover, transit observations provide limited information about spatial variations in atmospheric properties or surface conditions. Direct imaging represents the ultimate goal of exoplanet characterization, actually taking pictures of distant worlds and analyzing their light directly. This technique could reveal seasonal variations, weather patterns, surface compositions and biosignatures without relying on favorable orbital geometries. The fundamental challenge is contrast. Rocky planets typically appear 10 billion times fainter than their host stars at visible wavelengths. This is equivalent to trying to photograph a firefly hovering next to a searchlight from a distance of several thousand miles. Advanced coronagraphic techniques are required to suppress starlight while preserving the planetary signal. Ground-based telescopes equipped with adaptive optics and specialized coronagraphs have achieved the first direct detections of young, massive exoplanets orbiting far from their stars. The VLT, Very Large Telescope in Chile, directly imaged the four-planet system around HR 8799, revealing giant planets 5 to 10 times Jupiter's mass, orbiting at distances of 15 to 70 astronomical units. These early direct imaging successes focus on young planets that are still warm from their formation, making them bright enough to detect in infrared light. Mature planets like those in our solar system remain beyond the reach of current ground-based coronagraphs due to atmospheric turbulence and instrumental limitations. Space-based coronagraphy offers the potential to image mature, potentially habitable planets around nearby stars. NASA's Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will carry a coronagraph instrument designed to demonstrate high-contrast imaging technologies. While primarily a technology demonstration, the Roman coronagraph may detect reflected light from giant planets in nearby systems. Future dedicated exoplanet imaging missions could revolutionize our understanding of potentially habitable worlds. Proposed concepts include large space telescopes equipped with internal coronagraphs or external star shades, specially shaped spacecraft that fly in formation with telescopes to block starlight while preserving planetary signals. Direct imaging would enable spectroscopic analysis of reflected sunlight from exoplanet surfaces and atmospheres. Such observations could detect biosignatures like oxygen and ozone produced by photosynthetic life, or industrial pollutants that might indicate technological civilizations. The technique could also reveal surface features, cloud patterns, and seasonal variations that provide insights into planetary climate and habitability. The development of direct imaging capabilities requires pushing technology to unprecedented limits. Coronagraphic systems must suppress starlight by factors of 10 billion, while maintaining stability over hours-long observations. Adaptive optic systems must correct atmospheric turbulence with precision measured in nanometers. Despite these challenges, steady technological progress suggests that direct imaging of potentially habitable exoplanets will be achieved within the next 2 decades. The concept of habitability extends far beyond the simple calculation of orbital distance from a star. While the habitable zone provides a useful starting framework, determining whether a planet can actually support life requires understanding complex interactions between stellar radiation, atmospheric composition, planetary mass, magnetic field strength, and geological activity. Consider the fundamental requirements for life as we understand it. Liquid water serves as the universal solvent for biochemical reactions, but its existence depends on surface pressure and temperature conditions that allow water to remain stable in liquid form. On Earth, water exists as liquid across a temperature range from 0 to 100 degrees Celsius at standard atmospheric pressure, but this range expands significantly under higher pressures or contracts under lower pressures. Atmospheric pressure itself depends on planetary mass and atmospheric retention. A planet must be massive enough to gravitationally bind a substantial atmosphere, yet not so massive that it accumulates a thick hydrogen envelope like the gas giants in our solar system. Current models suggest that planets with masses between 0.5 and 10 times Earth's mass represent the optimal range for retaining atmospheres while maintaining rocky compositions. The atmospheric greenhouse effect plays a crucial role in determining surface temperatures. Earth's average surface temperature is approximately 33 degrees Celsius warmer than it would be without greenhouse gases in our atmosphere. Carbon dioxide, water vapor, and methane trap outgoing infrared radiation, creating a warming effect that extends the habitable zone boundaries both inward and outward from their purely radiative limits. However, greenhouse effects can become runaway processes under certain conditions. Venus likely experienced a runaway greenhouse effect early in its history, where increasing temperatures caused more water to evaporate, which increased atmospheric opacity to infrared radiation, leading to further warming until all surface water was lost to space. Understanding the conditions that lead to runaway versus stable greenhouse effects is critical for assessing exoplanet habitability. Planetary magnetic fields provide another crucial factor for habitability. Earth's magnetic field, generated by convection in our planet's liquid iron core, deflects harmful charged particles from the solar wind and prevents atmospheric stripping. Mars lacks a global magnetic field and has lost most of its atmosphere over geological time. Planets orbiting close to active stars, particularly red dwarfs, face intense stellar radiation that could strip atmospheres unless strong magnetic fields provide protection. Stellar activity also influences habitability in complex ways. Young stars produce intense ultraviolet radiation and frequent flares that can sterilize planetary surfaces and drive atmospheric escape. However, moderate levels of stellar activity might actually benefit life by providing energy sources for prebiotic chemistry and maintaining atmospheric mixing. The TRAPPIST-1 system stands as perhaps the most intensively studied example of potentially habitable exoplanets. Located 39 light-years from Earth, this ultra-cool red dwarf star hosts 7 Earth-sized planets, with 3 orbiting within the star's habitable zone. The system's compact architecture places all 7 planets closer to their star than Mercury orbits our Sun, yet the star's low luminosity maintains temperate conditions on the outer worlds. TRAPPIST-1, E, F, and G occupy positions where liquid water could theoretically exist on their surfaces, but each faces unique challenges. TRAPPIST-1e receives stellar flux similar to Earth's, but its proximity to the red dwarf star means it likely experiences tidal locking, with one hemisphere permanently facing the star and the other in eternal darkness. This could create extreme temperature gradients unless thick atmospheres redistribute heat efficiently. Recent observations with the James Webb Space Telescope have begun constraining atmospheric properties in the TRAPPIST-1 system. Initial results suggest that TRAPPIST-1c lacks a substantial atmosphere, possibly due to atmospheric stripping by stellar radiation. These findings highlight the challenge of atmospheric retention around red dwarf stars, which remain active and produce damaging radiation for billions of years longer than Sun-like stars. Kepler 442b represents another intriguing habitability candidate. This super-Earth, with a radius 1.34 times that of Earth, orbits within its Sun-like host star's habitable zone every 112 days. The planet receives stellar flux about 70% that of Earth, placing it in a potentially temperate regime where liquid water could exist with appropriate atmospheric conditions. The challenge with super-Earths like Kepler 442b lies in understanding their atmospheric evolution. Planets significantly more massive than Earth can retain thick hydrogen atmospheres inherited from their formation, creating mini-Neptune environments unsuitable for surface habitability. Alternatively, if these planets lose their primordial atmospheres, they might develop secondary atmospheres through volcanic outgassing, potentially creating Earth-like conditions. Proxima Centauri b, orbiting the nearest star to our Sun, exemplifies both the promise and challenges of habitable zone planets around red dwarfs. With a minimum mass 1.3 times that of Earth and an orbital period of 11.2 days, this planet orbits within its star's habitable zone at a distance of just 0.05 astronomical units. The planet's proximity to Proxima Centauri subjects it to stellar radiation flux up to 400 times more intense than Earth experiences from our Sun during stellar flares. The host star produces frequent high-energy flares that could strip planetary atmospheres and sterilize surface environments. However, recent modeling studies suggest that planets with substantial atmospheres and strong magnetic fields might survive in such environments. The search for life on exoplanets requires identifying biosignatures, observable phenomena that provide compelling evidence for biological activity. The most promising approach involves spectroscopic detection of atmospheric gases that are produced by life and would not persist in planetary atmospheres without continuous biological production. Oxygen represents the most widely discussed biosignature for several compelling reasons. Free oxygen is highly reactive and would quickly disappear from planetary atmospheres through chemical reactions with surface rocks and atmospheric compounds. Earth's oxygen-rich atmosphere exists only because photosynthetic organisms continuously produce oxygen at rates that exceed its chemical destruction. Detecting significant oxygen concentrations in an exoplanet atmosphere would therefore provide strong evidence for biological activity. However, oxygen detection faces significant challenges and potential false positives. Oxygen can be produced through abiotic processes, such as photodissociation of water vapor in planetary upper atmospheres, followed by hydrogen escape to space. This process could potentially create oxygen-rich atmospheres on planets that have lost their surface water, creating false biosignatures. The simultaneous detection of oxygen and water vapor would strengthen biosignature claims, since abiotic oxygen production typically occurs at the expense of atmospheric water. Additionally, detecting oxygen alongside other gases like ozone only one, provides further confirmation, since ozone forms from oxygen through photochemical processes and creates distinctive spectroscopic signatures. Methane, carbon tetrahydrogen, represents another important biosignature candidate. On Earth, approximately 90% of atmospheric methane derives from biological sources, including anaerobic bacteria and larger organisms. Methane has a relatively short atmospheric lifetime, typically destroyed by reactions with hydroxyl radicals within decades, so its presence requires continuous replenishment. Abiotic methane production can occur through geological processes, particularly serpentinization reactions between water and ultramafic rocks. However, the simultaneous presence of methane and oxygen creates a compelling biosignature argument, since these gases react rapidly with each other and would not coexist in significant concentrations without continuous production by distinct biological processes. Phosphine, phosphorus trihydrogen, has emerged as a potentially powerful biosignature following its controversial detection in Venus's atmosphere. This gas is highly reactive and quickly destroyed by photochemical processes, yet it is produced by anaerobic bacteria on Earth. The Venus phosphine detection remains disputed, but it has focused attention on phosphine as a biosignature for anaerobic life in planetary atmospheres. Industrial pollutants represent a novel class of potential technosignatures, evidence for technological civilizations rather than simple biological activity. Gases like nitrogen dioxide, nitrogen E-dioxide, or chlorofluorocarbons have no known natural sources and would provide unambiguous evidence for industrial activity if detected in exoplanet atmospheres. The challenge of biosignature detection lies not only in achieving the spectroscopic sensitivity required to detect trace atmospheric constituents, but also in developing robust criteria for distinguishing biological from abiotic sources. This requires comprehensive understanding of planetary atmospheric chemistry, geological processes, and the full range of environments where life might emerge and persist. The transformation of exoplanet research through citizen science represents one of the most remarkable developments in modern astronomy. Traditional scientific research had always been conducted by professional scientists with access to specialized equipment and training, but the digital age has democratized astronomical discovery in unprecedented ways. The Planet Hunters project, launched in 2010 through the Zooniverse platform, recruited volunteers to visually inspect light curves from NASA's Kepler mission. The project's success stemmed from recognizing that human pattern recognition excels at identifying subtle or irregular signals that automated algorithms might miss. While computers efficiently detect regular periodic signals, human eyes can spot unusual transit shapes, single-event transits, or complex periodic patterns that indicate interesting astrophysical phenomena. The first major citizen science discovery came in 2012, when volunteers Kian Jek and Robert Galliano identified unusual signals in the light curve of star Chi-C 84628552. Their discovery led to the confirmation of PH1b, Planet Hunters 1b, a circumbinary planet orbiting two stars within a quadruple star system. This discovery demonstrated that motivated amateurs could make genuine contributions to cutting-edge research. The PH1b system presented extraordinary complexity that challenged conventional understanding of planetary formation. The planet orbits a close binary star pair every 138 days, while this binary system orbits a more distant binary companion every 1,000 years. The gravitational dynamics of such systems create complex perturbations that could destabilize planetary orbits, yet PH1b maintains a stable configuration. Citizen scientists have contributed to numerous other discoveries, including several planets missed by automated Kepler processing pipelines. These successes highlight complementary strengths of human and computer analysis. Computers excel at processing vast data sets systematically, while humans excel at recognizing unusual patterns and adapting to unexpected phenomena. The educational impact of citizen science extends far beyond individual discoveries. Tens of thousands of volunteers have gained hands-on experience with real astronomical data, developing intuitive understanding of stellar variability, planetary transit signatures, and the challenges of distinguishing genuine signals from instrumental noise. Many participants have pursued further education in astronomy or related fields, creating a pipeline of scientifically literate citizens and potential future researchers. Projects like Galaxy Zoo, which classifies galaxy morphologies, and Radio Galaxy Zoo, which identifies radio sources, have expanded citizen science into numerous astronomical research areas. The success of these projects demonstrates that distributed human intelligence can tackle scientific problems that remain challenging for automated analysis. The exponential growth in exoplanet data volume has driven rapid advancement in artificial intelligence and machine learning applications. Modern exoplanet surveys generate terabytes of data annually, containing millions of stellar light curves that must be searched for planetary transit signals. Traditional analysis approaches become computationally intractable at such scales. Machine learning algorithms have proven particularly effective at distinguishing genuine planetary transits from false positives caused by binary star eclipses, stellar activity, or instrumental artifacts. Convolutional neural networks, originally developed for image recognition, have been adapted to analyze time series photometric data with remarkable success. The AstroNet neural network, developed by Google AI in collaboration with NASA, achieved significant breakthroughs in processing Kepler data. The system successfully identified 2 previously undetected planets in the Kepler 90 system, making it the first known 8-planet system beyond our own solar system. This discovery demonstrated machine learning's capability to extract signals from data that had been thoroughly analyzed using conventional techniques. Deep learning approaches have also revolutionized the characterization of false positive signals. Traditional methods required time-intensive human review of each candidate signal, creating bottlenecks in survey pipelines. Neural networks trained on large datasets of confirmed planets and false positives can now automatically classify signals with accuracy approaching that of expert human reviewers. Automated vetting algorithms have become essential components of modern exoplanet discovery pipelines. The TESS mission processes data from hundreds of thousands of stars using sophisticated algorithms that identify periodic dimming events, assess their statistical significance, and prioritize candidates for follow-up observations. These systems must balance sensitivity, detecting genuine planetary signals, with specificity, avoiding false positive contamination. Machine learning techniques are also being applied to atmospheric characterization problems. Neural networks trained on synthetic spectra can rapidly analyze transmission spectroscopy data to infer atmospheric compositions, temperatures, and cloud properties. These approaches enable systematic analysis of large samples of exoplanet atmospheres that would be prohibitively time-intensive using traditional fitting methods. The integration of artificial intelligence into exoplanet research represents more than just computational efficiency gains. Machine learning approaches can identify subtle patterns in data that might escape human analysis, potentially revealing new types of planetary systems or atmospheric phenomena. As data sets continue growing exponentially, AI-assisted analysis will become increasingly essential for extracting scientific insights from observational data. Exoplanet research has evolved into a truly global enterprise involving space agencies, universities, and research institutions across all continents. This international collaboration reflects both the enormous technical challenges of exoplanet detection and the universal human fascination with finding other worlds. NASA's exoplanet missions have established the United States as a leader in space-based transit surveys, but European contributions have been equally significant. The European Space Agency's upcoming Plato mission will conduct the most comprehensive survey of Earth-like planets around Sun-like stars, using 26 cameras to monitor hundreds of thousands of bright stars with unprecedented precision. The Plato mission incorporates several technological advances that build upon lessons learned from previous transit surveys. The mission will measure stellar oscillations, asteroseismology, to precisely determine stellar ages, masses and radii. This information is crucial for characterizing any planets detected, since planetary properties are inferred from transit depths and stellar parameters. Ground-based contributions from international collaborations have been essential for validating space-based discoveries. The High-Accuracy Radial Velocity Planet Searcher, HARPS, spectrograph at La Silla Observatory in Chile has confirmed hundreds of exoplanets through radial velocity measurements. Its successor, HARPSON, at the Telescopio Nazionale Galileo in Spain, continues this work with improved precision. The MERTH project represents innovative international collaboration in ground-based exoplanet searches. This network of small telescopes in Arizona and Chile continuously monitors nearby red dwarf stars for transiting planets. Despite using modest equipment compared to major space missions, MERTH has discovered several important planets, including LHS 1140b, one of the closest known transiting planets. Chinese contributions to exoplanet research are rapidly expanding with ambitious future missions planned. The China Space Station telescope will conduct wide-field surveys for planets and other astronomical phenomena. Additionally, ground-based spectrographs at Chinese observatories are contributing radial velocity measurements for planet conformation and characterization. Competition between research groups has historically driven rapid progress in exoplanet discoveries. The race to find the first exoplanet around a Sun-like star motivated competing teams to push technological capabilities to new limits. This competitive environment continues today in the search for potentially habitable planets and atmospheric characterizations. However, the enormous technical challenges of modern exoplanet research increasingly favor collaborative approaches over pure competition. Space missions cost billions of dollars and require international partnerships to achieve their scientific goals. Ground-based follow-up observations require coordinated efforts across multiple observatories and time zones. The most significant discoveries now typically result from collaborations involving dozens or hundreds of researchers from many institutions. Data sharing has become increasingly open and collaborative in exoplanet research. NASA makes Kepler and TESS data publicly available immediately upon processing, enabling researchers worldwide to contribute to discoveries. The Exoplanet Archive serves as a central repository for confirmed exoplanet properties, providing standardized access to the global community. This collaborative approach has accelerated the pace of discovery, while ensuring that important findings receive thorough validation from multiple independent research groups. The result is a more robust and reliable foundation for our understanding of exoplanet populations and properties. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, represents NASA's next flagship mission for exoplanet discovery and characterization. Named after NASA's first chief astronomer, often called the Mother of Hubble, Roman will carry a 2.4-meter telescope with a field of view 100 times larger than Hubble's, enabling unprecedented wide-field surveys of our galaxy. Roman's primary exoplanet science will come from gravitational microlensing surveys a technique that complements transit and radial velocity methods by detecting planets at all orbital separations around stars throughout the galaxy. When a star passes precisely between Earth and a more distant background star, its gravity acts as a lens that magnifies the background star's light. If the lensing star has planets, they create additional magnification spikes that reveal their presence. The microlensing technique offers unique advantages for planetary detection. Unlike transit and radial velocity methods that favor planets in close orbits, microlensing is most sensitive to planets at orbital separations similar to those of Jupiter and Saturn in our solar system. The technique can detect planets with masses as small as Mars orbiting stars thousands of light-years away, providing statistical insights into planetary populations throughout the galaxy. Roman's microlensing survey will monitor approximately 200 million stars toward the galactic center, where stellar densities provide optimal conditions for lensing events. The mission expects to detect over 1,000 new exoplanets, including the first statistical sample of planets with masses and orbits similar to those in the outer solar system. The mission will also conduct the first comprehensive census of rogue planets. Worlds that have been ejected from their birth systems and now drift freely through interstellar space. Current planetary formation models predict that gravitational interactions during system assembly should eject significant numbers of planets, but observational confirmation has been limited due to the extreme difficulty of detecting isolated planets that emit no light. Roman's coronagraph instrument represents a crucial technology demonstration for future direct imaging missions. The coronagraph will attempt to directly image reflected light from giant planets orbiting nearby stars, suppressing starlight by factors exceeding 100 million. While primarily a technology pathfinder, the instrument may detect several dozen planets and provide our first direct spectroscopic measurements of their atmospheres. The coronagraph's success will validate key technologies needed for future missions designed to image Earth-like planets. These include deformable mirrors that correct optical imperfections in real time, advanced wavefront sensors that measure microscopic distortions, and sophisticated data processing algorithms that extract planetary signals from residual stellar light. The European Space Agency's Planetary Transits and Oscillations of Stars (PLATO) mission, launching in 2026, represents the most ambitious ground-based transit survey ever conceived. Using 26 individual cameras mounted on a single spacecraft, PLATO will monitor up to 1 million stars simultaneously, searching specifically for Earth-sized planets in Earth-like orbits around Sun-like stars. PLATO's design addresses key limitations of previous transit missions. While Kepler demonstrated that small planets are common, most of its discoveries orbit stars that are too faint for detailed atmospheric studies. PLATO will focus on bright nearby stars where detected planets can be subjected to comprehensive follow-up observations using ground-based telescopes and future space-based instruments. The mission's astroseismology program will revolutionize our understanding of stellar properties by measuring minute oscillations in stellar brightness, caused by sound waves propagating through stellar interiors. These measurements provide precise determinations of stellar masses, radii, and ages with accuracies approaching 1%, far superior to conventional methods based on stellar photometry and spectroscopy. Precise stellar characterization is crucial for exoplanet studies because planetary properties are inferred from transit observations combined with stellar parameters. A 10% uncertainty in stellar radius translates directly to 10% uncertainty in planetary radius. Plato's asteroseismology measurements will enable precise characterization of planetary sizes, densities, and compositions. The mission's observing strategy involves long duration pointing towards two primary fields for at least 2 years each, plus shorter observations of additional fields. This approach balances the need for long baselines to detect planets in Earth-like orbits with the desire to survey large numbers of stars for statistical completeness. Plato expects to detect thousands of new exoplanets, including the first large sample of true Earth analogues. Rocky planets with radii between 0.8 and 1.2 times Earth's radius orbiting in the habitable zones of Sun-like stars with periods between 200 and 400 days. These discoveries will provide crucial constraints on the frequency of potentially habitable worlds in our galaxy. The mission will also characterize multi-planet systems with unprecedented precision, revealing the detailed orbital architectures that constrain planetary formation and migration theories. Plato's long observational baseline will detect planets with orbital periods up to several years, accessing the realm of temperate planets that remain beyond the reach of current transit surveys. The next generation of ground-based telescopes will revolutionize exoplanet characterization through direct imaging and high-resolution spectroscopy. The Extremely Large Telescope, ELT, currently under construction in Chile, will feature a 39-meter segmented primary mirror that collects 16 times more light than current 8 to 10-meter telescopes. The ELT's enormous light-gathering power, combined with advanced adaptive optics systems, will enable direct imaging of exoplanets at separations as small as a few astronomical units from their host stars. The telescope will directly detect reflected light from potentially habitable planets around the nearest dozen Sun-like stars, providing our first glimpses of alien worlds similar to Earth. Adaptive optics technology has advanced dramatically over the past decade, progressing from simple systems that correct atmospheric turbulence using single guide stars to sophisticated multi-conjugate systems that provide wide-field correction using multiple laser guide stars. The ELT will employ the most advanced adaptive optics system ever built, using thousands of actuators to correct atmospheric distortions hundreds of times per second. The Giant Magellan Telescope, GMT, featuring 7 8.4-meter mirrors arranged in a configuration equivalent to a 24.5-meter telescope, will provide complementary capabilities for high-resolution spectroscopy of exoplanet atmospheres. GMT's unique design enables simultaneous observations at multiple wavelengths, crucial for detecting multiple atmospheric constituents and distinguishing biological from abiotic sources. The 30-meter telescope, TMT, designed with a 30-meter segmented primary mirror, will conduct systematic surveys of nearby stars for directly imaged planets. TMT's coronagraphic instruments will achieve contrast exceeding 10 to the power of -10, enabling detection of reflected light from planets receiving stellar flux similar to Earth. These ground-based giants face significant challenges from atmospheric turbulence and thermal emission, but their enormous collecting areas provide crucial advantages for spectroscopic characterization. Direct imaging from the ground requires aggressive starlight suppression techniques, but successful demonstrations have already directly imaged several young giant planets orbiting at large separations from their host stars. NASA's concept for a future habitable worlds observatory represents the ultimate goal of exoplanet science, a space telescope specifically designed to image and characterize potentially habitable planets around nearby Sun-like stars. This mission would employ a large primary mirror, possibly 8 to 15 meters in diameter, equipped with advanced coronagraphic instruments capable of suppressing starlight by factors exceeding 10 billion. The Habitable Worlds Observatory would conduct comprehensive atmospheric characterization of dozens of potentially habitable planets, searching for biosignatures including oxygen, ozone, water vapor, and methane. The mission could provide definitive answers about the prevalence of life in our cosmic neighborhood and establish whether Earth represents a typical or exceptional outcome of planetary evolution. Technical challenges for such a mission remain formidable, requiring breakthrough advances in optical stability, vibration isolation, and coronagraphic performance. Alternative approaches, including starshade missions where a separate spacecraft flies in precise formation with a telescope to block starlight, may provide more feasible pathways to achieving the required contrast performance. The fundamental challenge confronting exoplanet science lies in the vast distances separating us from even the nearest potentially habitable worlds. Proxima Centauri b, the closest known exoplanet in its star's habitable zone, lies 4.2 light-years away. A distance so vast that light from the planet, travelling at the ultimate cosmic speed limit, takes over 4 years to reach our telescopes. At such distances, even the most powerful telescopes collect only a handful of photons from exoplanets during entire observation campaigns lasting months or years. An Earth-sized planet at Earth's orbital distance from a Sun-like star located 10 parsecs away would appear with an angular size of approximately 10 to the power of -11 arc-seconds, smaller than a coin viewed from the distance of Pluto. The photometric precision required to detect planetary transits pushes current technology to fundamental limits imposed by photon noise. Detecting an Earth-sized planet transiting a Sun-like star requires measuring brightness changes of 84 parts per million with statistical significance sufficient to distinguish genuine planetary signals from stellar variability and instrumental systematics. Stellar activity presents perhaps the greatest obstacle to detecting and characterizing small planets around Sun-like stars. Stars exhibit brightness variations caused by rotating star spots, magnetic activity cycles, and convective granulation that can mimic or mask planetary transit signals. The Sun's brightness varies by approximately 0.1% over its 11-year magnetic activity cycle, with short-term variations reaching several parts per thousand. These stellar variations create systematic noise that increases with observational baseline, making long-period planets around active stars particularly challenging to detect. Advanced statistical techniques, including Gaussian process regression and machine learning algorithms, are being developed to model and remove stellar activity signals while preserving genuine planetary signatures. Instrumental systematics represent another major source of noise in precision photometry. Space telescopes experience thermal variations, pointing instabilities, and detector aging that creates spurious brightness variations at levels comparable to planetary transit signals. The Kepler mission dedicated enormous effort to understanding and correcting instrumental systematics, developing sophisticated pipeline algorithms that enable detection of Earth-sized planets. Atmospheric characterization through transit spectroscopy faces even more severe signal-to-noise challenges. The spectroscopic signature of water vapor in an Earth-like planet's atmosphere produces signals at the level of 1 to 10 parts per million, comparable to the precision limit of current space-based instruments. Detecting biosignatures like oxygen requires even higher precision and careful control of systematic errors. The proliferation of exoplanet candidates from transit surveys has created an unprecedented challenge in distinguishing genuine planets from false positive signals that mimic planetary transits. Binary star systems can produce eclipse signatures virtually identical to planetary transits, requiring sophisticated analysis techniques to achieve reliable discrimination. Hierarchical triple-star systems present particularly insidious false positive scenarios. A small star eclipsing a larger companion in a distant binary can produce transit-like signals when observed in blended light with a foreground star. The eclipse depth and duration may match those expected for a planetary transit, but the object creating the signal is actually a star with mass hundreds of times larger than any planet. Background eclipsing binary stars create another class of false positives when their light blends with that of the target star. Even when the binary system contributes only a small fraction of the total observed flux, its eclipses can create apparent transit signals attributed to the brighter foreground star. High-resolution imaging is often required to identify such contaminating sources. Instrumental artifacts can also create convincing false positive signals. Charge transfer inefficiency in aging CCD detectors, thermal variations affecting photometric stability, and data processing errors have all produced candidate signals that initially appeared to represent genuine planetary transits. Rigorous validation procedures are essential to identify such artifacts before claiming planet discoveries. The statistical validation approach developed for the Kepler mission provides a powerful framework for assessing the reliability of planet candidates without requiring extensive follow-up observations. This method calculates the probability that a candidate signal represents a genuine planet versus various false positive scenarios, taking into account stellar properties, galactic structure, and binary star statistics. However, statistical validation remains controversial for individual planet claims, particularly for potentially habitable worlds where confirmation carries extraordinary scientific significance. The recent debates surrounding the claimed detection of phosphine in Venus's atmosphere illustrate the challenges of validating marginal signals in noisy data where systematic errors may not be fully understood. Ground-based radial velocity follow-up provides the gold standard for planet confirmation, but this approach becomes increasingly difficult for small planets around faint or active stars. Current spectrographs can achieve velocity precisions approaching 1 meter per second, but stellar activity often produces larger systematic variations that can mask or mimic planetary signals. Current exoplanet detection methods suffer from severe selection biases that distort our understanding of true planetary populations. Each technique favors different types of planets, creating a highly non-uniform sampling of the actual distribution of worlds orbiting other stars. Transit surveys are most sensitive to large planets orbiting close to their stars, since such planets produce the deepest transit signals and have the highest probability of producing transits as viewed from Earth. The geometric probability that a randomly oriented planet will transit its star as seen from Earth decreases as 1 over orbital distance, making detection of planets in Earth-like orbits approximately 50 times less likely than detection of planets in Mercury-like orbits. Radial velocity surveys exhibit complementary biases, showing greatest sensitivity to massive planets in close orbits where their gravitational influence on the host star is strongest. The velocity amplitude induced by a planet scales as planetary mass divided by orbital distance, strongly favoring hot Jupiters over Earth-like planets in temperate orbits. These selection effects have historically led to overestimation of hot Jupiter occurrence rates and underestimation of small planet frequencies. The early dominance of hot Jupiter discoveries created initial impressions that such extreme planets were common, when in fact they represent less than 1% of all planets around Sun-like stars. Direct imaging surveys face opposite selection biases, detecting only young, massive planets at large orbital separations where they are sufficiently bright and well separated from their host stars to enable direct detection. This technique is blind to the vast majority of planets, including potentially all Earth-like worlds around mature stars. Gravitational microlensing provides the most unbiased sampling of planetary populations, since its sensitivity depends primarily on planetary mass rather than orbital configuration or stellar properties. However, microlensing events are rare and typically non-repeatable, making detailed characterization of detected planets extremely difficult. The incomplete nature of current planet searches means that our census of exoplanets remains heavily biased toward easily detectable worlds. Statistical techniques are being developed to correct for these biases and infer the true underlying distribution of planetary properties, but significant uncertainties remain. Most critically, no survey has yet detected a planet that truly matches Earth's size, mass, orbital period, and stellar environment. The much-sought Earth twin may exist among the thousands of known exoplanets, but our detection methods have not yet achieved the sensitivity required to find it. Whether this reflects the rarity of Earth-like worlds or simply the limitations of current technology remains one of the fundamental open questions in exoplanet science. The search for Earth 2.0 requires establishing precise criteria that distinguish genuine Earth analogues from planets that merely share some terrestrial characteristics. A true Earth twin must match our planet across multiple fundamental parameters: size, mass, orbital characteristics, stellar environment, and atmospheric properties that enable surface habitability. Size constraints for Earth analogues typically require planetary radii between 0.8 and 1.25 times Earth's radius. This range excludes super-Earths that might retain thick, hydrogen-dominated atmospheres unsuitable for surface habitability, while also excluding sub-Earths that might lack sufficient gravity to maintain substantial atmospheres over geological timescales. Mass determinations remain challenging for most exoplanets, requiring precise radial velocity follow-up that pushes current spectrographic capabilities to their limits. Earth-mass planets orbiting in habitable zones around Sun-like stars induce stellar velocity variations of only 9 centimeters per second, smaller than typical walking speed and approaching the fundamental limit imposed by stellar surface convection. The orbital requirements for Earth analogues extend beyond simple habitable zone membership to include orbital eccentricity and period constraints. Earth's nearly circular orbit maintains relatively stable insolation throughout its annual cycle, while highly eccentric orbits could produce extreme seasonal variations incompatible with stable surface climates. Additionally, the orbital period must be long enough to maintain temperate conditions, typically requiring periods between 200 and 400 days for Sun-like host stars. Stellar characteristics impose additional constraints on true Earth analogues. The host star should be similar to our Sun in mass, temperature, and age to provide stable energy output over billion-year timescales required for complex life evolution. Stars, significantly more massive than the Sun, have shorter lifespans that may preclude biological evolution, while much lower mass stars produce different radiation spectra and may subject close-in planets to damaging flare activity. Atmospheric requirements for habitability include the presence of substantial atmospheres capable of greenhouse warming while avoiding runaway greenhouse effects. The atmosphere should contain water vapor, indicating the presence of surface oceans, but not be dominated by thick carbon dioxide layers like Venus. Ideally, atmospheric oxygen would indicate active photosynthetic life, though oxygen could potentially result from abiotic processes. Current observational capabilities cannot yet characterize all these parameters for any single exoplanet. Even the most detailed atmospheric studies require multiple space-based observations spanning months or years, while precise mass measurements demand years of radial velocity monitoring with the world's most sophisticated spectrographs. The detection and characterization of true Earth analogues requires revolutionary advances in observational capabilities across multiple domains: photometric precision, spectroscopic stability, angular resolution, and contrast performance. Each improvement opens new regions of parameter space for potential Earth twin discoveries. The James Webb Space Telescope represents current state-of-the-art capabilities for exoplanet atmospheric characterization, but even Webb cannot detect biosignatures in Earth-like atmospheres around Sun-like stars. The required spectroscopic precision exceeds Webb's capabilities by factors of 10 to 100, depending on the specific atmospheric constituent and stellar brightness. Next-generation space telescopes will require primary mirrors significantly larger than Webb's 6.5-meter aperture to achieve the light-gathering power necessary for Earth analog spectroscopy. Concepts under study include 15 to 30-meter space telescopes that would dwarf all existing space-based observatories, requiring revolutionary advances in deployable mirror technology and precision optical control. Starshade technology offers an alternative approach to achieving the extreme contrast ratios needed for direct imaging of Earth-like planets. A starshade is a specially shaped screen that flies in precise formation with a space telescope, positioned to block light from the target star while allowing light from orbiting planets to reach the telescope unimpeded. The required formation flying precision for starshade missions exceeds anything previously demonstrated in space. The starshade must maintain its position relative to the telescope with accuracy measured in centimeters across distances of tens of thousands of kilometers, while the telescope simultaneously tracks target stars with milliarc-second pointing precision. Ground-based extremely large telescopes will contribute complementary capabilities for direct imaging of the brightest Earth analog candidates. The extremely large telescope's 39-meter primary mirror, combined with advanced adaptive optic systems, will achieve angular resolution approaching that of space telescopes while providing far greater light-gathering power for spectroscopic characterization. Artificial intelligence and machine learning will play increasingly critical roles in extracting Earth analog signals from noisy observational data. Neural networks trained on synthetic planetary spectra can identify subtle spectroscopic features indicative of biosignatures, while accounting for stellar contamination, instrumental systematics, and atmospheric noise that plague conventional analysis methods. The development of photonic technologies offers promising avenues for achieving unprecedented spectroscopic precision. Laser frequency combs provide ultra-stable wavelength calibration that enables radial velocity measurements with precision approaching 10 centimeters per second, sufficient to detect Earth-mass planets in Earth-like orbits around nearby Sun-like stars. Space-based interferometry represents the ultimate frontier for exoplanet imaging. potentially enabling direct detection of continents, oceans, and seasonal variations on nearby Earth analogues. Concepts under study include arrays of space telescopes flying in precise formation to create virtual instruments with effective baselines extending hundreds of meters. Current statistical analyses of exoplanet populations provide optimistic predictions for Earth analog discovery rates once observational capabilities achieve the required sensitivity. Extrapolations from Kepler results suggest that approximately 20 to 50% of Sun-like stars host planets between 0.8 and 1.25 Earth radii, with orbital periods between 200 and 400 days. These occurrence rate estimates imply that true Earth analogues should exist around several hundred Sun-like stars within 100 light-years of Earth, a volume containing approximately 15,000 Sun-like stars. However, the geometric probability of observing transits reduces the number of detectable transiting Earth analogues to perhaps 10 to 20 systems accessible to current and near-future transit surveys. The Plato mission, with its focus on bright Sun-like stars and multi-year observational baselines, represents our best near-term prospect for discovering transiting Earth analogues. Mission simulations predict detection of 10 to 50 Earth-sized planets in habitable zones around Sun-like stars, depending on final mission configuration and observational strategy. Ground-based radial velocity surveys are approaching the precision thresholds needed to detect Earth-mass planets in temperate orbits around the nearest Sun-like stars. The combination of improved spectrograph stability, advanced data analysis techniques, and multi-year observational baselines should enable detection of several Earth analog candidates within the next decade. Direct imaging surveys using ground-based extremely large telescopes may achieve first light detection of reflected starlight from Earth analog candidates by 2030, though detailed atmospheric characterization will require more advanced instrumentation. Space-based direct imaging missions capable of comprehensive biosignature searches remain at least 15 to 20 years in the future. The convergence of multiple detection and characterization techniques provides redundant pathways to Earth analog discovery. While transit surveys offer the most comprehensive statistical sampling, radial velocity and direct imaging approaches will provide crucial confirmation and detailed characterization of the most promising candidates. Machine learning analysis of existing datasets may yield Earth analog discoveries hidden in archival observations. Sophisticated algorithms trained on synthetic data can potentially extract signals below the noise thresholds of conventional analysis techniques, particularly when combining data from multiple observational epochs or wavelength bands. The confirmed detection of a true Earth analog would represent one of the most significant scientific discoveries in human history, fundamentally reshaping our understanding of planetary formation, biological evolution, and our place in the universe. The implications extend far beyond astronomy into philosophy, theology, and human culture. From a scientific perspective, Earth analog discovery would provide crucial constraints on planetary formation theories and the conditions required for habitability. Detailed atmospheric characterization could reveal whether Earth-like planets typically develop oxygen-rich atmospheres through biological processes, or whether alternative atmospheric compositions can support surface habitability. The detection of biosignatures in an Earth analog atmosphere would constitute the first definitive proof of extraterrestrial life, answering one of humanity's most fundamental questions. Such a discovery would revolutionize astrobiology and potentially provide insights into alternative biochemical pathways and evolutionary processes. Conversely, the absence of detectable biosignatures in multiple Earth analog atmospheres would suggest that complex life may be extraordinarily rare in the universe, supporting rare Earth hypotheses and highlighting the exceptional nature of our planet's biosphere. This outcome would carry profound implications for conservation efforts and our responsibility as potentially the only technological civilization in our cosmic neighborhood. The cultural and philosophical implications of Earth analog discovery extend well beyond science. Confirmation that Earth-like worlds are common would support the Copernican principle that Earth occupies no special position in the universe, while potentially rare Earth scenarios would emphasize our planet's unique status and precious nature. Religious and philosophical traditions would face fundamental questions about the nature of life, consciousness, and humanity's role in creation. The discovery of life beyond Earth would challenge anthropocentric worldviews, while potentially supporting ideas about universal principles underlying biological evolution. The technological developments required for Earth analog discovery will yield numerous applications beyond astronomy. Ultra-precise optical control systems, advanced materials, and sophisticated data analysis algorithms developed for exoplanet research will find applications in fields ranging from medical imaging to quantum computing. As we stand at this unprecedented moment in human history, the scope of our achievement in exoplanet science appears almost miraculous when viewed against the backdrop of our cosmic insignificance. In just 3 decades, we have progressed from knowing only the 9 worlds of our solar system to cataloguing nearly 6,000 planets orbiting other stars, with thousands more awaiting confirmation. This transformation represents more than mere technological achievement. It reflects humanity's relentless drive to understand our place in the cosmic order. Every exoplanet discovery carries us closer to answering questions that have haunted human consciousness since we first gazed upward at the star-filled night sky. Are we alone? Is Earth unique? What does it mean to be human in an infinite universe? The numbers that now define our cosmic context would have seemed like science fiction to previous generations. Statistical analyses of exoplanet populations suggest our galaxy contains more than 100 billion worlds, a number so vast that if you counted one planet every second, it would require over 3,000 years to enumerate them all. Among these countless worlds, conservative estimates indicate that billions orbit within their stars' habitable zones, maintaining temperatures where liquid water could exist on their surfaces. Yet for all our remarkable progress, we remain tantalizingly close to, but not quite capable of answering the ultimate question. No confirmed Earth analog has been found among our catalogue of nearly 6,000 exoplanets. We have discovered worlds that share individual characteristics with Earth, similar sizes, comparable orbital distances, potentially habitable surface conditions, but no single planet that matches Earth across all the parameters that define our world's uniqueness. This gap between discovery and ultimate answers reflects the extraordinary precision required to detect and characterize true Earth twins. An Earth-sized planet orbiting in the habitable zone of a Sun-like star produces observational signatures at the very limits of current technology. Transit depths of 84 parts per million, radial velocity amplitudes of 9 centimeters per second, and atmospheric spectroscopic features at the level of parts per million all require instrumental capabilities that push physics and engineering to fundamental limits. The technical challenges confronting Earth analog detection have driven innovations that extend far beyond astronomy. The development of laser interferometry for gravitational wave detection, advanced adaptive optics for ground-based telescopes, and ultra-stable frequency combs for precision spectroscopy all trace their origins partly to exoplanet research demands. These technologies now find applications in fields as diverse as quantum computing, medical imaging, and autonomous vehicle navigation. The international collaboration required for modern exoplanet research has created unprecedented partnerships between space agencies, universities, and research institutions across all continents. The sharing of data, techniques, and discoveries has accelerated progress, while ensuring that the most significant findings receive thorough validation from multiple independent research groups. Citizen science contributions have democratized astronomical discovery in ways that would have been impossible in previous eras. Thousands of volunteers have contributed to genuine discoveries using nothing more than home computers and internet connections, proving that scientific research need not be confined to professional institutions with access to multi-million-dollar equipment. The psychological impact of exoplanet discoveries extends beyond their scientific significance into realms of philosophy, religion, and human culture. Each new world forces us to confront the likelihood that life exists elsewhere in the universe, challenging anthropocentric worldviews and expanding our conception of what it means to be alive in an infinite cosmos. Young people today grow up in a universe known to teem with planets, where the question is not whether other worlds exist, but whether any of them harbor life. This represents a fundamental shift in human consciousness, comparable to the Copernican revolution that displaced Earth from the center of the universe, or Darwin's recognition that humans evolved through natural selection rather than special creation. The next decade promises to bring us tantalizingly close to definitive answers about Earth's uniqueness in the universe. The James Webb Space Telescope is already probing the atmospheres of exoplanets with unprecedented detail, while future missions like Plato and Roman will survey hundreds of thousands of stars for Earth-like planets. Ground-based, extremely large telescopes will achieve direct imaging of potentially habitable worlds around nearby stars. Advanced artificial intelligence and machine learning techniques will extract subtle signals from vast data sets, potentially discovering Earth analogues hidden in observations that have already been collected. The convergence of multiple detection and characterization methods provides redundant pathways to the ultimate discovery, ensuring that when we find Earth 2.0, the detection will be robust and undeniable. The implications of confirming Earth analog existence extend far beyond academic astronomy into questions of cosmic biology, planetary habitability, and the frequency of technological civilizations. If Earth-like worlds prove common, the universe may teem with life in forms we can barely imagine. If such worlds prove rare, Earth's biosphere may represent an almost miraculous outcome of cosmic evolution. Either answer carries profound implications for how we understand our responsibilities as planetary stewards and members of a potentially rare or potentially common cosmic community. The discovery of life beyond Earth would revolutionize biology, philosophy, and our understanding of natural processes, while the absence of detectable life would emphasize Earth's precious and possibly unique status. As we approach this historical inflection point, we carry with us the accumulated wisdom and dedication of thousands of scientists, engineers, and citizens who have devoted their careers to unveiling the secrets of distant worlds. Their legacy, our legacy, will be remembered as the generation that first mapped the galaxy's planetary populations and took the initial steps toward detecting life among the stars. The race to find Earth 2.0 represents more than a scientific competition. It embodies humanity's deepest aspirations to understand our cosmic context and our place in the grand scheme of existence. Whether we discover countless Earth-like worlds or find that our pale blue dot represents a cosmic rarity, the answer will fundamentally reshape our understanding of life, intelligence, and meaning in an infinite universe. The greatest adventure in human history has only just begun. Above us, scattered across the infinite darkness of space, countless worlds await our discovery. Some may harbour oceans and continents. Others may be home to forms of life beyond our current imagination. A few might even host civilizations that, at this very moment, are looking back in our direction, wondering if they too are alone in the cosmic dark. The next chapter of this cosmic detective story remains unwritten, but one truth appears certain. We will not rest until we have answered humanity's most profound question. Are we alone? The answer lies out there, waiting among the stars, and we will find it.